Good morning, everyone. Welcome to MAE 209, Probability and Statistics. And we are now into Lecture 8. We have just completed our first quiz of the course, and that is being submitted through Moodle. And we'll have those marked shortly and returned to you. The questions should be similar to what you've seen both in class and on the assignments. Okay. So we're going to do some more examples of Bayes Theorem, and we'll also cover a topic called independence. So again, this is covering Bayes, this is in 2.4. And this would be covering section 2.5 in the textbook. So this is our example. Suppose a student either knows the answer or guesses when answering a question on a multiple choice quiz. The probability that the student knows the answer is P, and 1 minus P is the probability that the student guesses. If the student guesses at the answer will be correct with probability 1 over n, where n is the number of multiple choice alternatives. What is the conditional probability that a student knew the answer to a question given that he or she answered it correctly? Okay. So what we're going to do is we're going to define the event K such that the student actually knows the answer, and C be the event that the student answers correctly. So what I'm going to do is I start out with a tree diagram, and I'm going to use my two events here. I have K and K prime, so that's where they know and don't know the answer. And we also have C and C prime. Okay, so there's our probability tree. And the probability for K here, this is P. So the probability that they know it is P. And then 1 minus P would be that they don't know. And we also have, if the student guesses at the answer, so it means that they don't know. We're in this category right here, or this case. The probability that they get it correct would be 1 over n. Which then also means that the probability that they don't know it should be 1 minus 1 over n. Now, if they do know it, that means that they're going to get it correct with probability 1, because it's almost sure, and they won't have any probability of getting it incorrect. Yep. And as for the question someone is asking, 15 minutes was set up. No, it wasn't designed to you should have had, the idea was to have 15 minutes to complete the quiz. And there was 3 questions, 4 marks for each question, and the quiz is marked out of 10. Okay. So now we have, what is the conditional probability that a student knew the answer to the question given that he or she answered it correctly? So now what we need to do is the probability of K given C So what we can do then is we know that this is the case that we want. Here's K intersects C. So that would be P times 1 all divided by, so we would have P times 1 plus, so there's this case that we need here. We have the C. We also have this case here where we'll have K prime and C. So that is 1 minus P times 1 over N. I guess just kind of simplifying it without having to write the ones. And there's our answer. Okay, so that was the first example. Here's the second example. During a criminal investigation, the lead detective is 60% convinced that their prime suspect is guilty. Then a new piece of evidence is discovered that demonstrates that the perpetrator is left-handed. Experts say that only 10% of the world's population is left-handed. How sure is the lead detective now in light of this new information? Okay, so again, this is a Bayes theorem, and I would draw my diagram again. I should define my event, so I'll let G denote the event. That the prime suspect is guilty and, well, let's see, denote the event. That the prime suspect is guilty, or sorry, is left-handed. So we'll have G over here and G prime, and over here, over here. We have the probability that the investigator believes 60%, so 0.6 for guilt, which means that it's 0.4 for the complement, and we have some sort of characteristic left-handedness in this case. So we'll assume that, again, if they're guilty and they're left-handed, well then that the prime suspect is the actual perpetrator. We'll say is 1. We'll say it's 0 then if they're not left-handed. And we'll use that piece of information that only 10% of people worldwide are left-handed, and 0.9 if they're not. So what they're asking for is, how sure is the lead detective now in light of this new information? Well, what they're asking for is, what is the probability? So the detective believes that it's 60%. So we'll see what it changes after we calculate it. So again, we have 0.6 times 1 over 0.6 plus 0.4 times 0.01 which gives me 0.6 over 0.64. And if I grab a calculator, this gives me approximately 0.9375. So what this is saying is that the investigators believe has increased from 60% to almost 94%. About the quiz, are all the points in each question counted for the quiz mark? No. There was 4 marks for each question, which there was 3, so there was 12 marks, but we're going to mark it out of 10. Okay, so we've completed that. Oh, and then the other thing I'd point out for people that are concerned about the quiz is that if you feel that you didn't do very well on it, we do drop one of the quiz's marks. So just check the course outline to see for full details. So another piece of evidence is discovered that shows that the perpetrator has brown hair. In the world, 20% of human population has brown hair. How sure is the lead detective now? So what I'll do is I'll use G for guilty again. And I'll use B for brown hair. Okay. Are we assuming that the suspect has brown hair? Well, the perpetrator, this is the one that actually committed the crime, has brown hair. Now, that means that if the person is the perpetrator is guilty of the crime, then yes, they would also have it as well. So what this is, maybe I should say, is that the prime suspect is guilty. So if they're guilty, so they actually did do it, right? That means that they should also, that the perpetrator, which is the guilty party, should have brown hair. So that would be, probability would be 1 that they have brown hair and 0 if they don't. If they're not guilty and they didn't do it, but they could still have brown hair, the probability of that happening is 0.2 because 20% of the human population has it, and then 0.8 if they don't. Now, what is now our probability for this? The probability that the inspector thinks that this prime suspect is guilty. What do you say in the chat? What should I put on this branch right here? Yeah, 0.9375. Yes, that's very precise. I do like the 0.94, to be honest. Just a little easier. And then I would put down here the complement, which is 0.06. So this gives me 1 in total. So now we can calculate that probability. So this is the branch that we want. So 0.94 times 1 all over 0.94 plus. So this is the one that we need to look at. And where's my highlighter? So this is the branch that we needed. So again, because there's G and B. And then we need to do the summation of all the B's. So there's a B here. We also need this branch here. And that's how we're going to calculate that B. And I'm just color coding this at this point. There we go. So doing that, I get 0.06 times 0.2. So 0.94 over 0.94 plus 0.012. And can someone calculate that in the chat? 0.94 over 0.94 plus 0.012. Okay, yeah, that looks good. 0.9874. Everyone else got that? Okay. good to see there's confirmation. Okay, so what this means is that the investigator belief has increased from 94% to 99%. So that's what we usually do even in our daily lives, that as we get new information, our belief about something, the probability, and sometimes you'll hear people use their belief or subjective probability. As we get more and more data that confirms what we think, our belief starts to increase. So again, what we saw here was that there was a piece of evidence that showed that the guilty party, or that the perpetrator, was left-handed. And again, so it went up to 94%. And then when there was another piece of information that came in that the perpetrator has brown hair, well, now the belief increases. So what would be not Bayesian to do is to ignore that new information as it's coming in. So it's okay to update, in light of new evidence, your belief about something. So now we start something called independence, and this is following section 2.5 in the textbook. So far, what we had seen is that the probabilities, say, of A and B were not equal to each other. Meaning that if you had some more information given that B has occurred, it affects the probability of A, right? We just done something very similar, talking about with the inspector getting new information, again, is changing his probability. So this is what we'll call this is the conditional probability of A given B, and we'll call this the unconditional probability. And what this means is that the info, or the information, so the happened, resulted in a change in the probability of A. Okay, so that's what we've seen so far. Now, if we had the conditional probability, say the probability of A given B, then we'll say that they're equal. Well, what that is indicating is that given this information B, it didn't result in any change in the probability of A. So it had no effect on the probability of A occurring. Now, when we say that, we start to talk about the fact that A and B are independent. That A doesn't affect B, and B doesn't affect A. So this is our definition. So we have two events. We'll call them A and B. Are independent if, we'll use this definition up here. If the probability of A given B is the same as just the probability of A, then we call those independent. And the events are dependent otherwise. So recall from lecture 7, we had the multiplication principle. So we had the probability of A and B is equal to the probability of B times the probability of A given B. And we had done this example of what is the probability that you draw 2 queens from a well-shuffled deck of 52 cards without replacement. So I have a deck here, and assuming that there's 52 cards here, oops, get rid of those jokers. 52 cards, and there's 4 queens. So we had calculated that without replacement, that if I had a deck of cards, the probability that I draw a queen on the first is there's 4 queens available out of the 52 in total. So there was 4 out of 52. If I draw one, the probability that I have a second queen on the second draw, well, there's 3 remaining, and there's 51 cards now. So again, the event F depends on E. So this is an example of A and B. Oops, we're using E and F. E and F are dependent. Now, what this says is, let's consider this case. What is the probability that you draw 2 queens from a well-shuffled deck of 52 cards with replacement? So what that means is that you'll draw a card, and then you put it back into the deck. So we'll say let A be the event of the first queen, B be the event of the second queen, so what we're asking for then is the probability of A and B. So using our multiplication rule, we'll have the probability of A times the probability of B given A so here the probability of drawing a queen on the first card, there's 4 queens out of 52. Okay, but then you take that queen and you replace it back in the deck because it says with replacement. So this means that on the second one, the probability that you get a queen, well, there's still 4 of them, and it's still going to be a total of 52 cards. So it's 4 over 52. So you get 16 over 52 squared is 2,704. But what you're going to notice here is that the probability of A here, and this is the conditional probability, which was B given A, is still just the same as if I had calculated B. So because of this, we know that this is called the therefore symbol. So therefore, A and B are independent. So this leads us to a very interesting proposition. If you have events A and B are independent, if and only if that the probability of A and B is equal to the probability of A. But instead of writing the conditional probability, as again, if they're independent, well, it's the probability of A times the probability of B. So again, this is very important because a lot of people will start multiplying probabilities together, but you can only do that if they're independent. This is very important. Okay. So how does this proof go? It's very similar to what we have done up here. We'll start out with the multiplication principle, or the multiplication rule that we had learned from up here. So I'll copy that. Probability of B times the probability of A given B. So that's the multiplication rule. I'm going to just change the order. Just by commutativity. And by definition, going back to our other sheet here, so by definition, if two events are independent, if the probability of A given B is equal to A. Again, something important enough that I will put it in a box. So, by definition, again, if they're independent, so given A and B are independent, you can replace that just with the probability of A times the probability of B. And that's the end of the proof. Is there any questions about that so far? Basically, independence means that if I have two events, A and B, given that I know one of them, it doesn't affect the other. It doesn't change the probability. And we'll do this example right here. This one says, suppose that 40% of a company's kitchen range, it combines a kitchen range combines a stove and an oven in a single appliance. The kitchen range require service while under warranty. So that's 40%, whereas 20% of its refrigerators need such service. If a customer purchases both a range and a refrigerator manufactured by this company, what is the probability that both appliances will need service? So we've already kind of defined A and B. So we'll let A be that the kitchen range requires service while under warranty, and similarly for B, the refrigerator requires service. So again, this is what we were required. So what is required? Probability that both appliances need warranty. So that's the probability of A and B. So there's the and. That's the intersection. Okay. Now, how could I calculate the probability of A and B? What do you think in the chat? No? Anyone? So I have, someone is writing, okay. They're saying A times probability of B. So then they went and multiplied it together. 0.4. Which gives us 0.08. And what assumption did we make to get to that point then? Yes, Eric is making a good point. So we really should use the multiplication rule. So again, if we're starting out with the multiplication rule, yes, like everyone is pointing out, that A and B are independent. So you can make this like that. So you can replace it with that if A and B are independent. So, with this required, what we'll do up here, when we start to kind of outline here, we're going to write then, assume that A and B are independent. Sometimes that this can be a reasonable assumption that the kitchen range breaking down would be independent or doesn't affect the refrigerator breaking down. We could say that they are built by two different factories or two different lines, and we could say then that they're independent. So again, independence can be quite a strong assumption. Like you saw over here, when we were looking at the cards, if you're drawing two queens from a deck of cards, well, if you have with replacement, basically it means that the deck doesn't remember what you did. So if I picked a queen and I put it back in the deck and I picked another one, the probability hasn't changed. So again, what I'm doing on this doesn't affect the next time that I do something. Whereas if I start to do something with replacement, well, I can kind of say that the deck remembers what I did. So I picked one queen, and now I have 51 cards. Here's another queen, and now I have 51. Well, actually, now I'll have 50 in this card. So when I do the next one, so again, you can kind of think of it as that it doesn't really have any memory. So again, in this case, the range doesn't affect what happens to the refrigerator. Then we have this question: what is the probability that neither appliance will require service while under warranty? So what does that mean symbolically then? Just in the chat, can you write out what I need to calculate? What's the event that I need? Well, yeah. So there's a couple of people who there's some of the answers are correct too. So what I will do is I'll say neither appliance. So not A and not B. I want to point out though that we had done this previously, that A complement intersect B complement is equal to A union B complement. That's De Morgan's law. Yes, exactly. And we had done that in one of the previous lectures when we were dealing with Venn diagrams, and I had shown that this is true using Venn diagrams. So over here we can have the probability of A complement times the probability of B complement, which we know then is 1 minus the probability of A times the probability, 1 minus the probability of B which gives us 0.48. So again, independence is a strong assumption. Oops. So it's a strong assumption. You need to ensure that one event doesn't affect the probability of another. So let's say, for instance, there's, say, a father and you have a son. And there is, let's say that there's a certain number that is associated with the likelihood of heart disease. So let's say that, let's say probability of heart disease it may not be a good assumption if you think that the probability of heart disease for the father is independent of the son. Some of it is hereditary. So let's say if the father has heart disease, the probability of heart disease may be affected by the father's heart disease. So when we start to talk about people and we're saying that people are independent of each other, the probability of heart disease, well, if we start to look at within families, this may actually provide some information about the son. And because it may be affected, it could be that the father and son are dependent events. Whereas if you did a random sample, from a population, and these are not related, then you might want to test if they are independent. And sometimes this can make the calculation much easier to do. Does that make sense to the people that are in the chat? And lastly, we'll have independence of more than one event. Or more than two events. So again, the notion of independence of two events can be extended to collections of more than two events. Although it's possible to extend the definition for two independent events by working in terms of conditional and unconditional probabilities, it's more direct and less cumbersome to proceed along the lines of that last propositions that we did. And I'll just flip back to that. Back along these lines like this. Okay, so they say that we have events. We'll have A1, A2, all the way up to AN. In the book, they use mutually independent. Now that's if for K so we have 2, 3, all the way up to N. And every subset of indices we have, and then it's I1, I2, all the way up to IK. So again, every possible subset of those indices. Well, what they do is they say if for any of these kind of indices here, subset, so I have, let's say, I1, I2, so I'm taking any collection of the intersections, finite intersections. Then all I'm doing is I'm just taking these and multiplying them. Okay, and that's a lot of words, basically. So let me just to summarize the above. The events are independent. If the probability of any intersection so the probability of any intersection is equal to the product of the individual probabilities. Okay, someone has said I will check then the email after I've done the lecture. Okay, I'll keep an eye out for that. Thank you. So, independence of more than two events. So here is an exercise from the textbook. Now they use the proportions, but let's say the proportions of blood type in the US population are, so what they did was they had, what are the four types? We have A, we have B, there's AB, and O. And they say that the proportion of A is 0.4. For B, it's 0.11. For AB, it's 0.04. And 0.45 for O. So what they say is, assume that the blood type of two randomly selected individuals are independent of each other. So again, they're stating the explicit assumption of one another. is the probability of, and then let's do part A, which is both types are O. So in the chat, what do you think it is? What's the probability that if you randomly selected 2 people from the United States, what the probability would be that they're type O? Yeah. So what I would say is then it's the, say the probability of, I'll do O, I put O and then like a little 1 down here, and then the second person would be the probability of times the probability that the second person is O, 0.45 times 0.45. So yes, as some people have been putting in the chat, 0.45 squared and so I'm getting 0.2025. For part B, what is the probability that, or probability of, the blood types of 2 randomly selected people so 2 individuals and they match. Okay, so in this case the blood types of the 2 individuals have to match. So here is a technique. Again, we'll take cases. We have to find the, well, we could have where there's the first person is O and the second person is O, or the first person is AB and the second one is AB, or we could have the first person's B and the second person is B, and the last we could have that it's the first person is A and the second person is A. Yes, I think 0.38 is correct, but let's So to do that, it'll be the probability of the O's, that both are O's, that both are AB, that both are B, and both are A. So that would be, again, because they're independent of each other, we have O's, we have 0.45 times 0.45 plus, now we have the B's, so again there would be 0.04 times 0.04 plus, then we have the B's, 0.11 times 0.11 plus, and again last 0.4 and 0.4 for A. Yes. Oh, I'm a B, sir, for A. Oh, yes, thank you. There we go. And let me grab my calculator. So I'll double check. Move this up out of the way here. So I have 45 squared. I have 0.4 needs to be squared. We'll add that. We have 11 squared. We'll add that. And 0.4 squared, and we'll add that. So we get 0.3762. So again, if you randomly select two people, two U.S. Citizens, you know, from the population. The probability that they have the same blood type is approximately 38%, assuming the individuals are independent of each other. Like I said, that's a strong assumption, because if you started to do this inside of a family, the chances are that the family will have similar blood types. Okay, so just to go over what we had covered today. For lecture 8, we had gone over some examples of Bayes' theorem, and that's in section 2.4. We covered one where we looked at students doing a multiple choice test. We looked at an example where, given new information, that the subjective probability of something, of someone, can change in light of new evidence. So in this case, we had a lead detective looking at a suspect, seeing new evidence, and their belief increasing from 60 to 94% with new evidence. And similarly, as more come in, it just seems to increase for this. We then also touched into, well, we covered section 2.5. And again, it's an important concept in probability theory. This idea of independence, because so far we had seen examples where we had the conditional probability was not the same as the unconditional probability. Again, if you had more information that B, for example, the event B has happened, it resulted in a change of A. But if they are equal, that the unconditional is equal to the conditional is equal to the unconditional, then this introduces the idea of independence. So again, if they're equal, the conditional is equal to the unconditional, then they're independent. Otherwise, they're called dependent. We had two examples here where we had a dependent events, where we had it drawing without replacement with a deck of cards. So again, me drawing on the first and on the second without replacement does affect the probability. Whereas if I have it with replacement, me drawing a queen on the first draw or on the second one, it didn't affect it. So again, A and B are independent. We then came up with a test that if events A and B are independent, if and only if they satisfy this, that the probability of the intersection is equal to the product of the individual probabilities. Again, you can show up to a question like this, and you might not be able to calculate the intersection, the probability of the intersection, unless you make this assumption that they're independent. Again, independence is a very strong assumption. We talked about that as heart disease with a father and son. And it also could show up in here when we were looking at blood types in selected individuals. Okay, that's all the time that we have for today. Send emails if you have questions, further questions, send emails to my RMC account. Otherwise, enjoy the rest of the day, and I will see you on Tuesday. When can we expect to get feedback on quiz 1? Soon. Some people, maybe even as soon as Tuesday. I'm not sure yet. Okay. Thank you. Take care, everyone.